English compulsory usage. It is not happening. Slowly, we may have to switch over, but when that happens, we don't know. So today we are very grateful to Professor T.S. Pranesh for giving us a talk on physics of clouds, an introductory talk. So he will speak for about 15 minutes, followed by a question answers session for about 10 minutes. So before he speaks, I request our Joint Secretary, Professor Ruddaswamy, to introduce the speaker. Over to you, Professor Ruddaswamy.
Yes, sir. Sir, thank you very much, sir, for extending this great opportunity. It is indeed a great honor and immense pleasure for me to introduce Dr. T.S. Pranesha, an eminent professor and distinguished speaker of today's online talk. Dr. T.S. Pranesha obtained his MSc degree in physics from Sri Krishnadevaraya University, Anantapur, and PhD degree in physics from Pune University. He held several positions such as Research Fellow, Research Associate, and Principal Investigator of Modeling Air Pollution and Networking Project in Indian Institute of Tropical Meteorology, Pune. Research Associate in University of Pune, Faculty and Head of the Department of Physics, CMRIT, Bengaluru, Professor and Head of Department of Physics, Controller of Examination, Coordinator of the activities of Nano Initiative, and Research Physics Laboratory, which are recognized as a research center by Vishweshwaraya Technological University, all in BMS College of Engineering, Bengaluru. Developed an aerosol laboratory which is listed in the achievement of Indian Institute of Tropological Meteorology, Pune, while he was a research student, and coordinated 2 intensive observation periods during his postdoctoral position at the same institute. His research interests include cloud microwave and aerosol processes. Number of PhDs supervised 3, international journal publication 25, conference papers 10. His important publications are on trend and international variability of Arabian Sea heat content in Journal of Marine Systems 2024, analysis of ozone photochemistry over southern tropical megacity Bengaluru, India in Journal of Photochemistry and Photobiology 2022, assessment of radon and thoron exhalation from soils and dissolved radon in groundwater in the vicinity of elevated granitic kill, Chikballapur district, Karnataka, India in radiation protection dosimetry 2020, field studies of scavenging of aerosols by rain events in Journal of Aerosol Science 2004, scavenging of aerosol particles by large water drops, wasp coefficients, half-lives, rainfall depths in Journal of Geophysics Research 1997. With this brief introduction, may I now request Dr. T.S. Pranesha, an eminent professor, kindly to speak on physics of clouds and an introduction. Over to you, sir, and thank you very much, sir. Thank you very much, sir.
Thank you very much. I've been honored to speak on this forum. I've been associated with the clouds for almost 3 decades. First 1.5 decade directly with the clouds. Later on, some aspects related to clouds. So today I'm going to talk about a kind of introduction to the physics of clouds. A lot of physics goes into the cloud formation and the precipitation. Even a student of physics is not generally exposed to the physics of clouds. So I feel it's very exciting. Let us see how we take it about. Let us start with definition of a cloud. How do we define cloud in meteorology? Cloud is an aerocolloid system with no visibility. If you stretch your hand right in front of you, you don't see it. That is the zero visibility. A cloud is an aerocolloid system. In the atmosphere, what clouds we come across, the suspended particles are water droplets. In the aerocolloid in atmosphere, where the suspended particles are water droplets, is a cloud. Let us look at formation of clouds. What is most important for formation of clouds is water vapor content in the air. At any given temperature, any particular mass of air has finite ability to hold water vapor. This finite ability, when it becomes saturated, we call it saturated vapor pressure. If the amount of water vapor reaches this threshold, it goes beyond this saturation vapor pressure, then the additional water vapor condenses. So this is what leads to a cloud formation. As the temperature increases, the ability of air to hold moisture increases, or we can say the saturation vapor pressure also increases with increase in temperature. So ultimately, the ways to reach saturation of an air parcel. Suppose you have a mass of air and there is already some water vapor content in that air. So if you want a cloud to form, that water vapor should saturate that air parcel. How do we achieve this saturation? There are two ways by which you can achieve this saturation. Either you add some water vapor from external sources or cool the air parcel. One of the two things will result in saturation. In atmosphere, the saturation of air parcel generally occurs by cooling through adiabatic ascent. Most often, the ascent of air masses are approximated to be adiabatic. So adiabatic ascent will cool the air parcel, and the amount of moisture present will at one particular height saturate the air parcel, resulting in formation of the cloud. In order to understand clearly the formation of clouds, we should in one way know the vertical temperature structure of the atmosphere. This shows the vertical structure of the temperature structure and pressure structure of the atmosphere. We can see here troposphere, and then stratosphere, mesosphere, etc. Cloud formation and rainfall is completely confined to troposphere. All weather activities happen within troposphere. Troposphere goes to a height of about 12 to 14 kilometers from the equator to polar region. So we are basically talking about the processes which happen within the troposphere. In troposphere, as you go up from ground to about 12 kilometers, the temperature decreases at a rate of about 9.8 degree Celsius per kilometer. This is called generally dry adiabatic lapse rate. This is a better picture of how the temperature varies with height or temperature profile. You can see the temperature decreases in troposphere up to a height of about 10 kilometers. Then the temperature has a different structure that we are not much concerned with when we talk about clouds. The second picture here, I need it for my discussion on the thunderstorms. So we need to talk about ionosphere. Ionosphere is a charged layer superimposed on the temperature structure of the atmosphere. In this, we can see that the ionosphere extends from about nearly 50 to 100 kilometer to about 1000 kilometer. That's a charged layer. This is very important when we talk about electrification of clouds in the atmosphere. Now, lapse rate is when an air parcel ascends, when it goes up in the troposphere, it cools. There are three ways by which it can happen. One is the adiabatic, dry adiabatic lapse rate. It's about 10 Kelvin per kilometer. Then if there is moisture in the given air mass, when it ascends, there are other processes which take place like condensation and others. So that leads to what we call moist adiabat or wet adiabatic lapse rate. It's about 6 Kelvin per kilometer. If there is no change in temperature, if air masses ascend, then it is called isothermal lapse rate. There will be no change. And isothermal lapse rates result in inversion. There will be no ascent of air masses. Generally in atmosphere, the ascent of air masses follow this dry adiabatic lapse rate. The cooling is about 10 Kelvin per kilometer. First we assume this and do the thermodynamic calculations. Subsequently, we bring in some small changes like pseudo-adiabatic, and we'll introduce some moisture in the calculations to look at the actual cloud thermodynamics. Now, the essential condition for the formation of clouds in the atmosphere is, as I said earlier, the ascent of air masses leading to saturation vapor pressure. So this is the main criteria for clouds to form in the atmosphere. This ascent can happen in one of the four ways that we'll come across in the latest slide. This cloud formation, when an air parcel ascends, it expands. When it expands, it cools. At a particular height, we call this as lifting condensation level in cloud physics. The water vapor, which is already present in the parcel, saturates the parcel, leading to condensation. Once the condensation happens, the heat of condensation is released, and this heat further warms the parcel, which continues to ascend. Once the condensation occurs, the droplets will start growing, and they grow up to about 20 micrometer by vapor diffusion. Later, the vapor diffusion will not be very efficient in the growth of the droplets. Subsequent growth of droplets happen by collision and coalescence process. Once the droplet reaches about 500 micrometer size through collisions and coalescence, these droplets will start falling under gravity. This leads to rainfall. Generally, we call rainfall as precipitation because precipitation is the combination of water phase as well as ice phase. So these droplets more than 500 micrometer, they start settling under gravity, leading to rainfall. Now, depending upon the in-cloud conditions, the type of winds present, the amount of moisture, and the aerosols, the droplet size spectrum evolves. Now, as I said, the ascent of air masses is an essential condition for the formation of clouds. There are four major ways by which air parcels can ascend. One is convection, convective ascent, then the frontal mixing, or the orographic ascent, or the large-scale convergence of air masses. That's what generally happens in monsoon rainfall. These are also the four main types of rainfall, which occurs globally. Okay. Now, in order to understand the four processes, that is convection, frontal mixing, orographic ascent, and the large-scale convergence, we need to know about the type of clouds. Clouds have a kind of classification. We classify them into three major categories. The higher level clouds, which form at the height of about 10 kilometers or so, they are called cirrus. And generally they have a hairy streak-like structure. The mid-level clouds, they are called generally altostratus or altocumulus, like that. So these altostratus clouds generally have layered appearance. They form in layers. And the third one is cumulus clouds, which are low level clouds. They are puffy and they always will be growing. We call them they look like cauliflower. If you see their tops, they look like cauliflower. So let us look at these clouds. We'll look at some photographs of them and come back to the convection and other processes. So these are the types of clouds at a glance. You can see these are small cumulus clouds, which are low-level clouds, and stratocumulus clouds, that is layered clouds with some development. Then stratus clouds are layered clouds. Then we have altostratus, that's mid-level layered clouds. Cirrostratus, that is high-level layered clouds. Cirrocumulus, high-level clouds with small developments like cauliflower. Then cirrus clouds, which are streak-like. And contrails are the condensation of the exhaust from aviation. Then we have cumulonimbus, which are cumulus clouds, which are very deep. The cloud base starts at about 1.5 kilometers in tropics. The cloud tops go up to about 10 kilometers. They touch almost tropopause. They are highly electrified. You get lightning and rainfall, sometimes hail form, hailstones, and nimbostratus are also charged clouds with rainfall, generally liquid rainfall. And fog is a ground level cloud which we come across during winter. So these types of clouds at a glance. And these are the actual photographs of clouds. The first one is stratus. You can see some cumulus activity also, some growth. That's called stratocumulus. Then the second photograph are cirrus, and some layers also are there, that is stratus clouds. So these are the actual photographs, and these are the photographs of cumulus clouds. Both are cumulus clouds. Uh, Generally, if cumulus appears, if conditions are good enough, within 20 minutes, these clouds will start raining. But both these clouds which I have photographed did not result in rainfall, saying that the conditions were not conducive for the development of the cloud. It just formed and dissipated. Then you can see cumulus clouds here in the bottom of this photograph, stratus clouds, the mid-level clouds, and we have cirrus clouds, which are the top level clouds. All the three in one frame you can see. Then this is a photograph in which there are a lot of small cumulus clouds. They are called cumulus humuli in cloud physics nomenclature. And in course of time, they combine and form what is called cumulus congestus. These cumulus congestus may turn into a thunderstorm. The entire process may take an hour or a few hours from the first appearance to the formation. From the first appearance of a small cloud to the start of the rainfall. So this is a cloud with rain associated with low pressure system, monsoon low pressure system over Arabian Sea. This is photographed at NCPOR, that is National Center for Polar and Oceanic Research at Goa. Even date is there. You can see this rain shaft over the sea. So these are generally the cumulonimbus clouds. There will be a lot of lightning and heavy rainfall over that area. Now let us come back to the ways the convection happens, the ways the ascent of air masses happen. The first one is convection. Moist air masses very close to the ground during summer, especially in tropics, they get heated up, they rise. When they rise, they cool as they ascend. The cooling is generally approximated as dry adiabatic lapse rate, leading to convective clouds. These clouds are cumulus clouds, which we have seen earlier. They are cumulus or cumulonimbus. Nimbus is the word which is associated with rainfall and lightning. Whenever a cloud has both the things, when it is highly electrified and it's raining, such clouds have the name nimbus. And they are highly electrified with lightning activity. The rainfall is showery. Suddenly it will start raining and it changes quite rapidly. Convective clouds, and the range is very limited. Sometimes in Bangalore we can see it will be raining in Basungudi but will not be raining somewhere in Jayanagar area. So it's very limited extent, and the precipitation is sometimes very heavy and for a short time. Most of the precipitation in tropics in our area is convective. So it's not widespread, it will be localized. You can see the schematic of how convection happens and convective clouds develop. And the second one is frontal mixing. This generally happens in subtropics. In subtropics, we have air masses coming from polar region. They're called polar fronts, and air masses coming from the equatorial region. They're called tropical fronts. Generally, the tropical fronts are more moist, they're warmer. And the fronts which come from polar region are cold. When they meet, the warmer tropical fronts will rise. It leads to the rising motion. And this rising motion, they're already moist, will result in the saturation of the air masses. This generally results in layered clouds. So stratified clouds, stratiform clouds, and most of the rain in Europe and subtropics is result of this frontal mixing. and they can be easily predicted. That's the reason that the rainfall predictions in subtropics is much more accurate than what we can generally do through models in tropics. This orographic ascent is due to the topography. Uh, there can be ascent of air masses uh, along with the mountain slopes. The air masses are lifted up on one side of the uh, mountains, and once they are lifted up, they attain saturation. There will be condensation, cloudiness, and precipitation. In mountainous parts of the world, uh, we generally have this type of orographic ascent and rainfall. And the other side of the mountain, it is called rain shadow area. That's what we experience in plains of India here, especially in southern India. The Sahyadris act as the regions for orographic ascent, whereas the other side of the Sahyadris, we generally have lesser rainfall. And this is a very interesting thing to talk about. Large scale convergence also leads to upward motion of air masses. The sea breeze from the Indian Ocean will come over the Indian subcontinent. Because there are Himalayas, the air masses cannot go further north, so they are stopped by Himalayan orography. So the air masses converge over a continental scale. Over entire India, they converge. So since they converge, there will be upward motion, and this sea breeze from Indian Ocean is already moisture laden. Lot of moisture they pick up when they cross over to the northern hemisphere, because northern hemisphere will have summer during March, April. So moisture is picked up by the air masses when they cross over from southern Indian Ocean to the northern Indian Ocean. These air masses converge, resulting in ascent of air masses. The moisture present will lead to cloudiness over continental scale. So this leads to precipitation. All our monsoon rainfall is basically large scale convergence along with local convection. So this makes the monsoon predictions much difficult because both effects are simultaneously present. Local convection along with large scale convergence of air masses. Large scale in the sense continental scale convergence it is. Cirrus clouds, which I talked about, also have a lot of optical effects. In this photograph, you can see the dispersion leading to some kind of appearance of colors through the cirrus clouds. And now I felt it is more appropriate to talk about thunderstorms. They are the special category of clouds which have a lot of rainfall and sometimes even the hailstorms, and they lead to a lot of lightning, and they sometimes are considered as indicators of climate change also. This particular slide shows what we call global electrical circuit. So I have shown that ionosphere, a superimposed charged layer over different layers of atmosphere, we can technically take it at the height of 100 kilometer. Ionosphere is always charged with respect to the ground. It is at a potential of 300 kilovolt with respect to ground, and it is at positive potential. Therefore, the air between the Earth and ionosphere is a dielectric. So it's a giant capacitor. There are leakage currents. Always there is current from ionosphere to Earth. We call it air to Earth current, or sometimes we call it air Earth current. It's about 1 to few picoampere per meter square. 1 to 2 picoampere per meter square. If you integrate this entire current over the surface of Earth, it amounts to about 200 amperes. Now, 200 ampere of current continuously flowing from ionosphere to Earth can completely discharge ionosphere, which is at 300 kilovolt with respect to Earth, in about 40 minutes. It never happens. Always the ionosphere is kept charged with respect to Earth. So this points to the process which keeps the charge back on the ionosphere. That is, ionosphere is always kept charged through some processes which happen in the atmosphere. So this charging process is considered to be through thunderstorms. Thunderstorms are the clouds which put back the charge on the ionosphere. So now let us look at thunderstorms uh, and see what causes them and what type of processes happen in lightning and related phenomena. This is what I've already described. We have thunderstorms, global thunderstorm activity always keeps the ionosphere charged. The other things I have already talked about. One thing which I want to just say is there is always an electric field uh, at the surface of Earth. It's about 120 volt per meter. Between our head and feet, there's nearly 140 volt of electric field. We don't feel any shock because the current is very low, 1 to 2 picoampere. We call them high impedance currents, and we can easily measure them. If you just put a point insulated from the earth, connect it to a sensitive electrometer, you can measure this current. Sometimes we were measuring them routinely at Indian Institute of Tropical Meteorology. Now let us look at thunderstorms. Thunderstorms are mainly the cumulonimbus and nimbostratus clouds. They are characterized by lightning, thunder, rainfall. They are highly electrified. Thunderstorms are characterized by 3 stages of formation and development. The first stage is called cumulus stage, the second one mature stage, and the last one is the dissipative stage of the storm. Let us look at them individually. This cumulus stage or cumulative stage of thunderstorm is the initial stage in which air masses start ascending. They're lifted upwards into the atmosphere, and there is some amount of moisture present in any air mass that will saturate the air parcel and condensation happens and clouds form. In this stage, you only have upward wind velocities, we call them updrafts in the entire air parcel. And this lifting condensation level in tropics, especially over India, is about 1.5 kilometer. The cloud base appears nearly at 1.5 kilometer. Using the first law of thermodynamics, we can even compute if we know the amount of moisture present in the atmosphere in that air parcel and the lapse rate at the given instant. If we know, we can estimate this lifting condensation level. That is where the cloud base appears. Then the second stage, that is mature stage. In the mature stage of a thunderstorm, the warmed air masses, they further ascend. They ascend till they come across an air mass which is warmer or kind of cap. There will be no chance of further ascent. This stage is almost at the tropopause. Tropopause acts as a kind of inversion which will not allow further ascent of this warm, moist air mass. Because it cannot ascend further, it will start spreading. So this spread will result in a kind of anvil. Anvil is a very important characteristic of thunderstorm. Any thunderstorm ultimately will have an anvil at the top, and there will be rainfall at the bottom. The resulting cloud is called cumulonimbus because it will have a lot of charges, and electrification will be at the highest. Very high electric fields form inside the cloud. The water droplets undergo a lot of collision coalescence and they develop into heavy droplets. And they also freeze because, as I said, these thunderstorms are very deep convective clouds. If the cloud bottom or lifting condensation level is 1.5 kilometer, the cloud tops reach as much as tropopause, 10 to 12 kilometers. So it's very deep convection. 0 degree isotherm is crossed, and the water droplets freeze become ice particles, and they start falling under gravity as rain, and when they start falling, they may melt, or sometimes if they are big enough, they may not even melt. These falling droplets will impart some weight to the air below, resulting in downdrafts. So the winds will start flowing out of the thunderstorm uh, bottom level, and the simultaneous presence of updraft and downdraft. Updrafts will always be there, and downdrafts will develop because of the weight of the precipitation. So the main characteristic of mature stage of a thunderstorm is presence of both updrafts and downdrafts simultaneously. And added to this, lot of turbulence develops within this thunderstorm. So this turbulence leads to strong winds and severe lightning sometimes, and at times they also get converted into tornadoes. Tornadoes are very intense vortices which are known to descend from the core of the thunderstorms. And this is a pictorial representation of mature stage of the thunderstorm. We can see the updrafts present, and we can see the downdrafts coming, and we can also see the formation of an anvil which gets extended horizontally compared to the bottom of the thunderstorm, thundercloud. And the last stage is called dissipation stage. In the dissipation stage of a thunderstorm, the cloud is dominated by the downdraft. If the atmospheric conditions are not enough to support the development of further thunderstorm cells in the neighborhood, this stage appears quickly, 20 to 30 minutes. The thunderstorm goes into dissipation stage. If we see properly, from the first appearance of one cloud in the horizon on a summer afternoon to the rainfall and dissipation, it should hardly take 30 minutes. Generally, this doesn't happen because by the time one thunderstorm cell reaches dissipation stage, the other cells start forming. They're called supercellular developments. Sometimes there will be a line of thunderstorms. They're called squall. This happens in Bengal in the month of Vaishakha. They call it Kal Baisakhi. Evenings will be generally dark with a lot of thunderstorms, and the thunderstorm activity starts at about 3 o'clock, goes up to 9 o'clock in the night. It's a series of thunderstorms. One place it will rain, and that formation of cells will continue, and there's a line of thunderstorms. So if in the case in which there are no supercellular development, a thundercloud or a thunderstorm cell will last for about 20 to 30 minutes. And the downdraft will push down all out of the thunderstorm. It will hit the ground and it will spread out. The downdraft is cooler. The cool air carried to the ground by the downdrafts cuts off the inflow to the thunderstorm, and the updrafts disappear and the storm dissipates. This is how one thunderstorm cell generally operates. The total time, as I said, is about 20 to 30 minutes. And there'll be a drop of about 4 to 5 degrees centigrade between the temperature prior to the start of the thunderstorm and after the thunderstorm. This schematic diagram represents all the three stages in one figure. We can see the cumulus stage where updrafts are there. We can see the mature stage in which updrafts along with the downdrafts are visualized. In the dissipation stage, the thunderstorm contains only the downdrafts, and the horizontal extent is about few square kilometers. And you can see this is 0 degree isotherm. The cloud tops go as deep as 10 kilometers. The temperature at that place is about minus 20 to minus 30 degrees centigrade, and that will definitely result in formation of ice phase in the cloud. This is a beautiful diagram, beautiful photo of an active thunderstorm. This is over Garajao, Madeira, Portuguese archipelago. We can see the cloud base we can see the cloud top, and there's a lightning. I think in cloud lightning, we can also see cloud to ground lightning. This is one beautiful photograph of a thunderstorm. Of course, this many thunderstorm cells active at a time. It is not a single cell. Now let us have a small look at the energy involved in thunderstorms. If we know the quantity of water which is condensed and subsequently precipitated from a cloud, then we can estimate the energy of a thunderstorm. In an average thunderstorm, if we do this exercise, it releases about 10 to the power 7 kilowatts hour of energy. That's 10 to the power 13 joule, which is equivalent to a 20 kiloton nuclear warhead. This is a single thunderstorm cell. But generally, there will be many cells in a given storm, and a large severe thunderstorm might have 10 to 100 times more energy than what it is. So generally, we say the energy involved in one thunderstorm activity is about 10 to the power 13 to 10 to the power 15 joule. And this schematic talks about the electrical structure of a thundercloud. If we take the thundercloud to be about nearly 10 to 12 kilometer deep, we see that the observations show that there is a tripolar structure in the thunderstorm. There's about 20 plus 20 coulomb charges at the top, plus 5 coulomb charges near the cloud base, and minus 20 coulomb charge in the middle of the cloud. This is the general structure. Rare observations have also predicted an opposite of it, but most often about 98% of the observations have shown this typical tripolar structure of the thunderstorm with plus 20 coulomb on top, minus 20 coulomb in the middle, and plus 5 coulomb at the cloud base. This leads to lightning. So this 20 coulomb, as we know, as physicists we know, it's a huge charge. So there will be dielectric breakdown of the air mass within, and if the electric field exceeds a particular value, there will be discharge, and that is the lightning. So lightning is the electrical discharge that occurs in a thunderstorm. It can be seen in the form of a bright streak or a bolt from the sky. Lightning occurs whenever electric field is built up within the cloud. When large enough charge is built, a large discharge will occur that can be seen as lightning. It's astonishing to know that the temperature of lightning bolt is nearly 30,000 Kelvin. It's almost 5 to 6 times the temperature of the sun, surface of the sun. The loud sound which we hear is due to the rapid adiabatic expansion of the air column around the lightning bolt, which is adiabatic. That rapid adiabatic expansion it is, and that expansion happens at speed of sound. So this is what gives us the huge sound, and the air around that lightning bolt gets instantly ionized, and there's an adiabatic expansion of the column. There are different types of lightnings. In-cloud lightning is very common. It is lightning which happens within the cloud, that plus 20, minus 20 coulomb, or minus 20 coulomb to plus 5 coulomb, or plus 20 coulomb to just some other charge if there is a neighboring cloud. This is in-cloud lightning. Cloud to ground lightning is a flash which happens from cloud base or the top of the cloud to the ground directly. And this is the one which poses a lot of threat to the life and property. And ground to cloud lightning is also possible when lightning bolt is initiated from the ground. Then cloud to cloud lightning, I have already said in the beginning, from one cloud charge center to another cloud charge center, there can be lightning. And there is a very peculiar type of lightning called ball lightning, in which people have observed a small ball, 20 to 200 centimeters wide, floating in air carrying plasma. So this is observed many times. And cloud to air lightning is when the lightning from a charge center of the cloud terminates in a charge, some kind of charge structure in the atmosphere. There are some possibilities that there are some apparent unbalanced charges in the atmosphere. So this cloud to air lightning is also observed when lightning terminates in the atmosphere, where there may be some charged centers due to some unexplained reasons. And let us look at some facts about lightning. A typical lightning involves currents more than 50,000 ampere. One lightning stroke carries nearly more than 50,000 amperes of current. So we can imagine I square R, even if R is very small, the amount of heat produced, Joule heating, is enormously large. It can burn a tree in seconds, it can be charged within seconds. Nearly 2,000 thunderstorms are active globally at any given time of the day. Even now, at this time of the day, 2,000 thunderstorms nearly are active globally. This is required for two things. One is the charge structure balance of the atmosphere, and also the energy and momentum balance of the atmosphere. And climatologically, there are nearly 40 lightning flashes per second globally. This particular aspect is sometimes taken as an indicator of climate change. If lightning flash density, flash per second, changes from around 40, which is the climatological value, we can talk about the climate change. So that's considered as an indicator of climate change. And how do thunderstorms get charged? These are some of the mechanisms which are proposed to explain the charging of the thunderstorm. I will not go deep into that because this itself becomes a topic for one or two lectures. These are contact electrification, electrochemical charging, influence charging, diffusion charging, and mechanisms involving freezing and splintering of air ice particles. And all these mechanisms operate individually or in a combined way, resulting in the tripolar structure of the thunderstorms, which I have shown earlier. So now, uh, which are the places which are vulnerable for lightning strikes, and what safety one can take it up? Isolated tall structures, isolated trees, isolated metallic fences, and mountain tops, open fields, open water bodies are few vulnerable places of lightning strike. And in order to avoid this danger during thunderstorm overhead, a reasonable hard roof is safer. If it is open field and if we don't have any shelter, it's advised to go to the lowest part of it. This is the only precaution which one can take. My PhD supervisor, Dr. A.K. Kamra, used to tell us that he was in New Mexico doing some observations of electric field changes during thunderstorms. So he had to lie down on the ground. Otherwise, New Mexico being a desert, no elevated structures used to be around that observation area. So he had to lie down with some waterproof jacket and display his instruments for taking observations. So that's the only way one can avoid the chance of being struck with lightning. So this clouds have both warming and cooling effect in the atmosphere. Uh, Warming effect is because they can absorb the terrestrial radiation. We call it OLR in meteorology, outgoing long wave radiation. Clouds can potentially absorb the outgoing long wave radiation or terrestrial radiation. This absorption warms up the earth. They can also cool by scattering or reflecting the In meteorology, short wave is considered to be visible plus ultraviolet. So they can reflect or backscatter the visible and ultraviolet radiation back into the space, and this can lead to cooling. So these are the both cooling and warming effects displayed by the clouds. Unfortunately, because of increase in the aviation in the recent days, a lot of contrail clouds form. This photograph shows the contrail clouds because of aviation, and the initial research activity shows that the contrail clouds are known to warm the atmosphere. So this is something which people are worried about. There is chance of further increase in the aviation sector. So this may lead to some kind of uh, problems in future. That's what the initial research indicates too. And thank you very much for your attention. This is a very small, very brief general introduction to the physics of clouds. If we can go deep into that, we need to have a clear knowledge of fluid mechanics because air masses move. We need to know about the Navier-Stokes equation. Once the condensation happens, the laws of thermodynamics come into picture. Once electrification happens, we also need to know about the electrodynamics. So with all this, I thank Professor Kadli, Professor Basuraj for giving me this platform to speak about the subject which I was involved with for last 3 decades. Thank you very much. I'll be more than happy to address some issues if people have. Thank you very much.
Thank you very much for a very informative and exciting talk about clouds. Now there is some time for questions. We'll go one by one. You may raise your digital hand and then we'll go accordingly. Already one hand is up. DK Srinivas Babu, you want to ask a question?
Yes, sir.
Please ask.
This is regarding the cumulonimbus clouds, which is very dangerous clouds for all our activities, UAV activities. Okay. Some of mishap also happened because of this cumulonimbus activities.
Okay.
Now, suppose if an aircraft is flying, when cumulonimbus clouds appear, then what is the way to avoid it? Suppose if you enter, my question is, suppose if you enter into the cumulonimbus clouds, then what happens? Whether it gives any pressure to the aircraft or it moves as if like the normal clouds only?
Okay. Generally, electrically, the aircraft is safe because it's a metallic enclosure. So electrically, it is safe. The problem comes only with the wind velocities. Generally, updrafts are okay. Pilots are trying to deal with the updrafts. They just circumvent that and go away. Downdrafts are considered to be potentially dangerous. So they are advised not to enter into the downdraft area of a thunderstorm because it will push the aircraft towards the earth. Otherwise, they are mostly trained to avoid the updrafts and downdrafts. Electrically, they are safe. That's the reason that aviation, by and large, it is safe, except for very few incidents involving thunderstorms.
All right. So one more question.
Okay.
See, I have observed that these thunderstorms at Chennai as well as the Balasur also. What I observed in Balasur, once the thunderstorm comes, it just comes like a dropping of a bomb for 1 to 2 minutes.
Okay.
1 to 2 minutes, it's horrible actually. And whereas in Chennai, it only a few seconds it comes and vanishes. Then what is the difference here and there?
Yeah, it is the initial conditions and the availability of moisture and the lapse rates. If initial conditions and the lapse rate are conducive, the growth is very quick. And the evolution of raindrop size spectrum is very fast.
Okay, we'll go on to the next question.
Yeah, it is just the initial conditions of the air masses.
Okay, thank you, sir.
Professor Umesh, would you like to ask?
Yes, sir. Good morning. I was wondering why there is a charge separation. Positive charges up at a greater height, and then negative charges a little below that.
Okay.
Something like a double layer formation. What is the origin for that?
That is the one which I just talked about in one of the slides towards the end of the presentation. It is one thing which people are debating even now. There are half a dozen charging mechanisms which are proposed, which ultimately result in the observed fact. But none of us, for over centuries, are able to explain why this tripolar structure appears and what is the actual cause of this. Half a dozen phenomena are proposed, but none of them, as it stands now, can completely explain this process.
The negative charge that you are showing, are they electrons or negative ions?
No, they are not ions. They are with precipitation. See, a raindrop generally carries some charge. So raindrops in thunderstorms, they carry about 10 to the power minus 12 to 10 to the power minus 10 coulomb. So it's raindrops or ice pellets. It is
Ice pellets. Yeah.
ice pellets. All are possible. And in atmosphere, we know that water drops remain as water drops up to minus 20 degrees centigrade unless they come across ice condensation nuclei. So this generally supercooled water droplets we call. So that is if they come across an ice condensation nuclei, they freeze, then charges appear. These are some of the mechanisms which are proposed. But as to answer your question, really speaking, we completely do not know what leads to this separation.
Okay, thank you.
I have just a follow-up question to what Professor Umesh was asking. You see, we always think that the ionosphere is overall neutral. But
Yes.
you are saying the bottom layer of the ionosphere has got so many kilowatts of 500 kilowatt voltage. Positively charged. How does it pick up that kind of positive charge?
That's what. Yeah, these thunderstorms, from the top of the thunderstorm to the ionosphere, there's a plasma discharge. They put back the charge onto the ionosphere.
Okay.
I forgot to mention that they're called sprites.
I see. Professor Malesh, would you like to ask a question? KS. Professor KS.
Yes, sir. Am I audible?
Yeah,
definitely. Yes, sir.
Go ahead.
Thank you, sir. Nice lecture. I want to know what contributes more for cloud formation. Does the land surface have any contribution, or only the oceans?
No, land surface definitely, because heating. See, all the processes of cloud formation involve heating of the ground, solar heating. So suppose, of course, solar heating, moisture, and the winds. For example, if the day is very strongly windy, that will not be good for the convection to start. If that is, say, summer afternoon, if surface winds are high, the convection is low. If there are no winds, convection can start. So the conditions which are required for cloud formation is surface heating, the surface winds, the presence of moisture, all these.
Okay. Do you move on to next question? Professor Keshamurthy.
Yes. Thank you very much for your nice. It's a very vast field. We can understand that. The thing is that does human activity, it may not keep the climate or the cloud formations in a constant cycle. So how does these greenhouse gases or large solar farms or environmental emissions have an impact?
Yeah, this has been studied quite elaborately. To answer your question in very brief, definitely the human intervention has made some changes in the climate. but quantification has still been not very easy. For example, if the emission of dust, aerosols, if aerosols increase in the atmosphere, I'll just tell you one example, that's all. Cloud condensation needs some kind of aerosols, some size spectrum of aerosols. If the number of aerosols is optimum, it is good for the cloud formation. If it is more than what is required, the number of aerosols on which cloud condensation, droplets can form, condense and form, will increase. If number of small droplets increase in a cloud, that is not good for the development of rainfall, because these droplets compete for the available water vapor. So the mere fact that you just increase the aerosols can lead to some kind of change in microphysics.
Yeah.
So that way, if greenhouse gases, for example, can lead to some, that's already documented, that there is a constant change in the temperature of the atmosphere. If time was there, I could have shown it. I don't have that. Observations clearly indicate there is some change. And this change, the work at Indian Institute of Tropical Meteorology suggests some things like what I am talking about. The cloud bases are okay, but cloud tops are little more deep. If convection is much deeper, and the radar soundings show that the raindrop size spectrum has shifted from what it should have been, like that, all the such things have happened, but that is not accounted for in the observations at the ground level. Still, we have reasonably good rainfall, but the pattern, they say, is shifting from the regular monsoon rainfall to a kind of episodic rainfall. Suddenly it rains for 1 or 2 days and it does not rain for 10-15 days.
Kind of chaotic.
They are attributing this to this type of changes, but not very clear. There's still a lot of work has to go on.
We move on to next question, please. Anyone else? We see nowadays very erratic rainfall, this pattern of distribution all over the world. Is it really an indication of global warming, or what do you think?
That's what I say. It is very early to talk about. Maybe the climatological pattern or the evolution of Earth itself might have been like this, because our observational history of meteorology is hardly 200 years. So we don't know what has happened in the past. But we cannot even rule out this possibility.
And they can. Okay. Thank you. Right.
Okay. Can you say a few words about the hailstorms and snowfall? You talked about rainfall. Under what conditions do we get the hailstorms and snow formation and all that? Briefly, if you don't mind.
Yeah, definitely. Let me first talk about the hailstorm. A typical thunderstorm over tropics in India, generally it is not a hailstorm. It's we get liquid water, precipitation. Hailstorms result in very deep convective clouds. When the droplets are settling under gravity, if the updrafts are very high, they're held within the cloud for a longer time, and they grow to a bigger size. And in case they come across the cloud, ice condensation nuclei, let me make it very clear, there are cloud condensation nuclei, ice condensation nuclei. Cloud condensation nuclei are essential for the formation of droplets. Ice condensation nuclei, they are required for the formation of ice phase of water in the cloud. Generally, the cloud droplets remain as water droplets down to the temperature of minus 20 degrees centigrade. They are called supercooled water droplets. The ice condensation nuclei in atmosphere are not many. They are very few. The moment one supercooled water droplet comes in contact with an ice condensation nuclei, that will freeze. The moment it freezes, the saturation vapor pressure over ice surface is lower than the saturation vapor pressure over liquid surface. So the Therefore, the ice pellets grow very fast compared to the liquid droplets. The ice phase, when it initiates, will spread very quickly in the cloud, and all droplets will freeze into ice. And if the conditions of the cloud are good enough, they start falling and they may not melt, and they reach the ground as the ice pellets itself. And sometimes it so happens that you have both liquid droplets as well as the solid precipitation. But there are occasions in which there is only solid precipitation. So this is again the in-cloud conditions which decide what type of precipitation we have. Convection should be very deep for ice phase to be present. During monsoon, generally we don't have. Pre-monsoon thunderstorms we have. Even post-monsoon it will not be there, because already Indian land mass will have cooled to certain extent during the monsoon, and the convective clouds in October, that post-monsoon thunderstorms, are not deep enough for the solid precipitation.
Professor Nagaraj, would you like to ask any questions?
Yes, sir. Sir, actually, according to the literature, from June 1st, southwest monsoon starts. But
Okay.
this year, a little early only. Any speculation for that, sir?
This year's forecast I have not still seen. See, this all atmospheric motions are quasi-periodic. They're completely quasi-periodic. Even cloud motions are quasi-periodic. Monsoon can come 15 days early, 15 days late. There are more than a dozen parameters globally identified on which the monsoon depends. Generally, this long-term forecast is given through statistical correlation technique. I have not, this year forecast I have not still seen. It is generally computed by one NCMWF, National Center for Medium Range Weather Forecasting, which is in Noida. They give a kind of indication about what may be the monsoon picture annually. I have not seen it, but this quasi-periodicity is very well documented. Monsoon can arrive sometimes 15 days early. Sometimes it has arrived even 1 month late.
Okay. Sir, one more doubt I have, especially
Yes,
about the lightning bolt temperature. You say around 30,000 Kelvin, and lightning current is of the order of 50,000 ampere.
Yes.
But it is only, lightning is only a spontaneous. How do they measure, sir?
We have techniques to measure it. Exact measurements we have done it. It is through change in magnetic field generally.
Anyway, thank you very much, sir, because you have taken a lot of effort to go through all these things, especially about you have explained in detail about the convection, frontal mixing, orographic ascent, and even large-scale convergence. So many definitions, and of course, even the students, if they are here, they have really understood about the physics of clouds. And
It's a pleasure, sir. When I was a student doing PhD, all these things were our daily affairs. So,
yes, sir, that's what, because in the syllabus, we normally don't have the physics of cloud and monsoon and other things.
yes.
But anyway, you have explained even starting from the definitions. I think Dr. Nataraju wants to say something.
Okay, please.
Yes, please.
Sir,
Okay, please.
sir, I have a question.
Yeah, please. Ask.
We often speak of cloud seeding.
Yes.
It's really useful. More often than it is a failure, I think.
Is it possible? Is it really practical? Just Just a joke.
What is, you want me to comment on this? Because I was wondering why no one has asked about cloud
What
seeding.
may be the,
Is it really useful?
what is the phenomenon that takes place?
Is there a basis for that?
Cloud seeding.
Yeah,
Sir, it will take some time to explain. Is it okay?
a few minutes, please.
Yes, sir.
Yeah, if one has to think about cloud seeding, there are, we should know about what type of clouds we are seeding. Basically, cloud seeding was suggested and first implemented in America by one Professor Bernard Vonnegut. In fact, Professor Bernard Vonnegut was the supervisor of my supervisor, Dr. Kamra. He was working with him. Bernard Vonnegut did a lot of extremely pointed scientific work in which he collected some ice pellets, melted them, studied what type of ice condensation, studied the structure of ice condensation nuclei. After a lot of trial and error method, he came to a conclusion that the silver halides resemble the structure of ice condensation nuclei in nature. So he suggested, suppose there is a very good, optimal cloud, which is about to rain but not raining. If you seed it with silver halides, that will act as ice condensation nuclei, result in ice phase, which leads to a lot of instability within the cloud, and it will start rainfall. This is the origin of cloud seeding. But this type of cloud seeding is recommended only for deep convective clouds, where the cloud tops are at a height of about 10 to 12 kilometer, where the temperature is minus 20 to minus 30 degrees centigrade. These clouds, of course, we can try them, and they have very limited horizontal extent. Their lifetime is very small. Whereas monsoon clouds are called warm clouds. Warm clouds, the entire monsoon clouds, if it is not combined with the cumulonimbus activity, will have only the water phase. It will never have an ice phase. So it is not appropriate to seed the monsoon clouds with silver halides. They're of no consequence. Therefore, people thought in a different way. They wanted to do seeding in a different way. They thought, if at all we can increase the size of the cloud droplets, we can probably create some more instability leading to precipitation. So what way we can increase the size of the liquid droplets? They thought we'll seed them with deliquescent salts like sodium chloride. The droplets absorb and they grow. It has been tried. In fact, the first cloud seeding operations in India were by Indian Institute of Tropical Meteorology. And in fact, they were by my PhD supervisor only. He was recruited for doing these operations, but they were suspended due to so many technical reasons. And that activity was not there throughout my stay at Indian Institute of Tropical Meteorology. It was almost 12, 13 years I stayed there. That was suspended. Now, people still try, as you have pointed out, it is very difficult to know has a cloud has rained because of the fact that we seeded it, or it has rained naturally, because it is very difficult to have control in the experimental area. See, atmosphere is so turbulent. If you seed in Bangalore, probably that seeding may have effect in Mysore. We don't know, because it's so well mixed. It's so dynamic. It is very difficult to really prove whether the rainfall has happened because of your seeding or naturally. There are some riders, but still some people have reported success in this. That much only I can talk about it.
Yeah.
Oh,
Okay, I think
thank
we are coming to. I request our.
Thank you very much, sir. You have explained a lot about.
I request our General Secretary to propose a vote of thanks.
Monsoon. And of course, from Karnataka Physics Association, we thank all the viewers, invitees, and even our KPA members. And we should also thank Dr. M.K. Raghavendra, who is providing the Zoom platform, and also Sai Venkataraman for providing the YouTube. Especially the students are presenting through YouTube.
Yeah.
And yes, other Professor Cogley and Dr.